Hi, and welcome to Train Signal. We're continuing our discussion of advanced services in the Windows Server 2012 release, and we're exploring here certificate authority technology. Digital certificates get used for a variety of purposes in the modern IT infrastructure. You might set up a VPN environment between two different locations for your organization, and the routers that connect those two environments together want to be able to communicate securely with each other, passing only encrypted data across that wire. Digital certificates are a very common technique to be able to configure those devices to be able to share that information securely. Highly secure email messages may require the use of digital certificates to be able to scramble the contents of the email for safety's sake. Certainly many of us are familiar with the Secure Sockets Layer, SSL, communication technology that will encrypt communication between a client computer and a web server so as to make sure that our bank balance transfer or our purchase from that website is done in a way that's secure, that doesn't allow confidential information to get into the hands of the bad guys. These digital certificates need to come from somewhere, and it turns out that the source is something called a CA, a Certificate Authority. So we're going to explore in this lesson how to create them, what they're for, and we'll explore the basics of how to use them to be able to provide a good, strong basis for security in a Windows environment. Now, to understand what a certificate authority does requires a little bit of background work. Certificate authorities provide a benefit referred to as a public key infrastructure. Now, to say a public key infrastructure, what does that mean? A public key is one part of a two-part mathematical pair of numbers, usually generated through the mathematics of large prime numbers. The mathematician nerds have found that certain interesting combinations of numbers have a very interesting property, that I can use one of those magic numbers to encrypt data in such a way that the only way to decrypt that data is with the other of those two numbers. Even the original number is not adequate to be able to undo that encryption. The encryption can be done using one of the two keys and can only then be undone with the other key. Public key encryption of this sort is something that's a relatively new technology. It really dates back only to the 1970s. What preceded that is a technique referred to as symmetric encryption, and that goes all the way back for literally millennia. The role of symmetric encryption is the same technique that you use when you walk out of your house in the morning. You use a key to lock your house. When you come back to the house, you let yourself back in with the same key. The same key locks and unlocks the same door. In the encryption world, I can generate a key, a numeric piece of data, use it to scramble some piece of data, and I can use that same key to unscramble it. The nice thing about symmetric key encryption is it's fast. I can easily generate a key. It's not terribly processor intensive to generate a random string of data with which to be able to encrypt some piece of information. The larger I make the string, the more secure the encrypted data is, the harder it is for the bad guys to hack into it. I can make it arbitrarily larger or smaller as need be, but there's a challenge with it. What if I encrypt some information and I want to send it to you? Well, you're going to need my key. So how do I send you my key? Well, I could just email it to you. But of course then anybody could intercept that key. Okay, so what I need to do is put that key in a file and encrypt it. Well, if I encrypt it with symmetric key encryption, I now have a new key to send to you. So what do I do with that key? Well, I can put that key inside of another file and encrypt that. But if I'm using symmetric key encryption, there's another key that I need to protect. I had a next door neighbor growing up who had a key to be able to get in and out of their house. They wanted to make sure that it was protected and kept safe so they could find it if they came home and had lost their other key. They wanted to have a backdoor, a hidden key to be able to get in their house with. So they took their house key and put it inside of a little magnetic box. You can hide these things under your bumper of your car or things of that sort. They took this magnetic key box and stuck it to their front door. They had a symmetric key problem. They wanted to have a easily accessible key that would let them in the house, but they ended up making it not much less vulnerable than it would have been if they just left it under their floor mat. So symmetric keys can be good for certain things. They're good for fast bulk encryption. If I want to do a large quantity of data encryption, symmetric key is definitely the way to go. It's fast, it's efficient, it can be arbitrarily strong based on how big of a key I throw at it. And even relatively small keys, 128 bits, 256 bits, 512 bits, are plenty large enough for most practical purposes for this symmetric key encryption. But the challenge is the idea of how do I get that information safely to you? How do I give the key to you in a way that lets you unencrypt data without running the risk of some third party picking up that symmetric key and using it against us? So the solution is public-private key encryption, a system of two keys, a so-called public key and a so-called private key, two different long strings of numbers, two different very large pieces of math that have a relationship to each other mathematically, but one that would take extraordinary amounts of processing effort over a period of years to be able to determine. Here's an analogy, maybe it helps. I lived for a while in an apartment complex, and in the middle of the apartment complex was a shared mail facility. Each apartment had its own mailbox, of course. Each mailbox owner, each renter, had their own key to get in their own mailbox. My key didn't open anybody else's mailbox for obvious reasons. Opened mine, though. When the letter carrier came to deliver mail in the middle of the day, that person didn't have a copy of all of our keys. That person had a separate key that opened up the back side of the unit, and the mail carrier could deliver mail that way. I had a key, the letter carrier had a key, and no matter how long I stared at my key, that would tell me nothing about what the letter carrier's key looked like. And likewise, the letter carrier couldn't tell what my key looked like by looking at his or hers. But because those two keys were related, they both had the ability to unlock one side or the other of my mailbox, I could exchange a secure communication with the letter carrier. The letter carrier could deliver messages that only I was able to receive. That's a little bit like what public-private key encryption is like. When the letter carrier delivered me mail, that person was using what you might think of as my public key. The letter carrier was sending me a message in a way that only I would be able to unlock. Likewise, when I wanted to go send a message to the outside world, I wanted the letter carrier to pick it up. I wanted to securely deliver that to the post office without having to physically be there to hand it to the representative. I used my public key to lock the piece of mail that I wanted to deliver inside my mailbox. The letter carrier would unlock that with the public key. That public-private key pair is dynamically generated mathematically by something called a certificate authority, a server whose job it is to be able to produce these mathematical pairs and assign them to particular individuals. If I want to be able to prove my identity to you by way of a digital certificate, I will find a certificate authority that's willing to produce for me something called a digital certificate. You can see how some of these puzzle pieces are now starting to fit together. A digital certificate is a logical binding between a public key and some description of some individual or some service. In many cases, it's a person. In the Windows environment, it's very common for users to contact a CA and request a user certificate. And the presence of that certificate on the user's computer proves that the CA seems to believe that that person is who they say they are. And therefore, anybody who trusts that CA therefore would trust that I am who I say I am because I have a certificate from that trusted CA that says so. So I will happily share my digital certificate with anybody who wants it. There's no secret information in that certificate. That certificate binds together my identity, my username, my email address perhaps if it's an email certificate, might bind together other interesting identifying information about a web server, things of that sort, and binds it to a public key. The whole idea of a public key is that it is public. It's meant to be shared. I will happily make available my public key to anybody who wants it. My private key, however, I will never share. Private keys are meant to be kept private, as you might well imagine, based on the name, and I never ever share that information with anybody. And that enables a couple of important behaviors. Remember that the private key can scramble things in a way that only the public key can unscramble. Not even the private key can unscramble something that was scrambled by itself, by the private key. Public key works the same way. Anything encrypted with the public key can only be unencrypted with the private key. Even the public key cannot decrypt something that the public key, just encrypted. Decryption must be done with the other half of the puzzle. So that means if you want to send a secure email to me, your starting point for that process is to locate a copy of my public key. If I've done a good job of using my public key infrastructure, I've given you my public key by giving you a copy of my digital certificate. which binds a copy of my public key to my identity in some fashion, my username, my email address, something. So in this case, let's assume it's an email certificate. So you use my public key, because everybody has my public key, and you use it to encrypt a message. That message can only be unencrypted by me, because it can only be unencrypted by the private key, and only I have the private key because I don't share that with anybody. With that idea in mind, you can send an encrypted message that nobody in the world except me can read. You've got a guaranteed secure delivery of that information. Let's take it the other way. If I have a message and I encrypt it with my private key, which only I have, and I send it to you, you can unencrypt it because you have a copy of my public key, because everybody does. Now you're thinking, well, wait a minute, that's not terribly secure. That means anybody can open that message. Yes. This is not a security technique that guarantees that the message will come securely to you. What this does, though, is something interesting. This is essentially what we might call a digital signature, where I have scrambled that message in such a way that can only be unscrambled with my public key. But think about what benefit you gain from being able to unscramble it with my public key. You learn for sure that that message is from me. That message could not possibly have come from anybody else except me, because nobody else but me can sign something with my private key. And only things encrypted with my private key can be unencrypted with my public key. And because it could be unencrypted with the public key, that means it was encrypted with the private key, which means it came from me. I hope you're starting to see the relationship between the public and private keys. They're kind of a matched pair of values. Maybe you might recall the story of little orphan Annie with the locket around her neck, or half of a locket around her neck. She knew that one day her mother, who gave her up for adoption, would come back and reclaim her and would bring the other half of that locket. And by putting the two pieces together, they would find each other and they would know that they belonged together. Public and private keys are like that. They have a matched pair sort of a relationship. They logically belong together mathematically, but in such a way that if you were to stare at any one of those two keys forever, you would never learn what the other one was like, not within thousands of years of computational effort. Few of us are willing to wait around long enough to see the outcome of that calculation. So with public and private keys, we can send secure messages, we can send authenticated messages, we can stitch those ideas together. I can take a message that I want to send to you, I can use your public key because you very wisely made it available to me, so I've now created a message that can only be read by you. I might take that message and encrypt it using my private key, because only I have that, and I might send that twice encrypted message to you. When you receive that message, you can unencrypt the first layer of encryption using my public key, which of course you do have because I wisely made it available to you, and that proves that the message came from me. But the message that you received is scrambled, because I've scrambled it deliberately in such a way that only you can unscramble it. Remember, I scrambled the content with your public key, which I have. You unscramble it with your private key, which only you have. You now have received a message that could not have been read by anybody else, and that could only have come from me. That latter benefit has a technical name called non-repudiation. It basically means I cannot come back later and say, oh, no, that wasn't me, I didn't send that. Because you can say, well, wait a minute, I unscrambled that message with your public key, which means it had to have been scrambled with your private key, and only you have your private key, therefore that message definitely came from you. If I continue to persist and say, no, I didn't send it, then my counterpart in the conversation says, well, if you didn't send it, and it was signed with your private key, then that means your private key has been compromised. Go get a new certificate from your CA, because somebody has gotten their hands on your private key, and therefore is able to impersonate you in digital communications. So CAs are commissioned to produce public and private key pairs of mathematical values, the binding of a public key with a description of some subject that the key applies to, an email account, a user account, things of that sort, is thereby a digital certificate. I can present a digital certificate to you as proof of my identity, and that will be meaningful to you only if you trust the CA that produced that certificate. If you know who runs that CA, and you trust that the operator of that CA only gives out certificates to people who are worthy of them, then you can safely assume that because the CA gave me my certificate, and you trust the CA, that therefore you can trust me. And therefore when I supply my certificate to you, you can trust that that is an accurate description of myself. The last piece of the puzzle there is digital certificate templates. Templates provide a way to be able to ask a CA for one of a number of different types of certificates. I might deploy a CA that's able to hand out EFS certificates, encrypting file systems, scrambles files on the hard drive. I might also configure that CA to supply email certificates. I might supply web server certificates, SSL style certificates. I might configure a secure FTP server. In each case, a template is called into service to describe the exact details of the certificate that I want to issue. Certificates, as we've seen, can be issued for a variety of different purposes. So let's get ready to install a certificate server and begin to experiment with some of this technology. To be able to install a certificate server principally requires two major decisions. The first one is to identify whether this CA is designed to be integrated with the Active Directory or not. If it is, there's a number of really interesting benefits available to us. We can configure an Active Directory integrated CA in such a way that if a user inside of that Active Directory domain requests a certificate, the Active Directory just instantly approves it. Approves the generation of the certificate, generates the public-private key pair, supplies the certificate to the user. It's a very logical thing to want to be able to do. I can, on an enterprise CA, customize the templates that I want to use. I can take an existing template, and if it doesn't suit my needs exactly the way that it is, and I can take that duplicated certificate template and customize it to suit the specific needs of my organization. In other cases, I might want to build a CA that is not tightly linked to Active Directory, where there is no Active Directory computer account for that CA. Because we don't have the built-in security features tied to Active Directory, that does mean now that any requests for certificates from that CA will have to be performed manually. Not that that's a bad thing. In some cases, that's a perfectly legitimate thing to do. We'll show you an example for that in just a moment. But it certainly is going to be additional work compared to the behavior of a CA that is Active Directory integrated. In other words, an enterprise CA. One interesting benefit of a standalone CA is that it is possible to keep it offline. You're thinking, what good could it be to have a computer that can hand out certificates but is turned off? Why would I want to do that? Well, the answer to that comes from the bottom of my slide here. Certificate authorities are set up either as a subordinate CA that lies logically below some other certificate authority, or it is the logical top of some hierarchy of CAs, in which case it is the root CA for that hierarchy of CAs. The root CA is at the top of a family tree of certificate authorities. Underneath that top-level root CA lies perhaps an additional tier of certificate authorities. In some organizations, those are the CAs that actually hand out certificates to those that need them. In some cases, they represent kind of a middle manager layer of CAs, configuring policies for yet a third, yet lower layer of certificate authorities, which actually hand out certificates to those that request them. The middle tier are then termed policy CAs. But what about this top-level CA, this root CA, and how does that relate to the idea of being standalone? One vitally important part of this whole CA infrastructure is this idea of trust. If I trust the root CA of an organization, then if that CA builds a digital certificate that says that I can trust some other lower-level CA, then I should be able to trust that lower-level CA because the parent CA, the top-level CA, says it's trustworthy. I trust the parent trusts the child, I should therefore trust the child. And again, it might well be that that CA has created a certificate for yet another CA further down the hierarchy. And I should trust that CA as well, seeing how I trust the root trusts the middle manager CA, the middle manager CA trusts the one at the bottom of the tree. That trust relationship critically requires the protection of the private keys associated with the digital certificates that identify the CAs themselves. An issuing CA, a CA that actually hands out certificates to individuals, has a certificate signed by its parent CA, probably a policy CA. The policy CA, the one that I keep calling the middle manager, has a certificate that's signed by the root. The root CA signs its own certificate. It is the top of my organization, PKI-wise, and therefore it has no higher authority to report to. It is the authority. So it uses a self-signed certificate. But consider what could happen if somebody were to somehow hack into that topmost CA. They could use it to issue certificates to those who don't deserve them. They could use that CA and revoke the certificates of people who should be able to continue using their certificates. If some individual compromised my CA, they could use it to create a certificate with which to create a subordinate CA able to create certificates that appear to be from that parent organization when, in fact, they might not be under the control of the IT organization for that company. That's an alarming idea. So how do we keep this organization secure? Well, one way to do it is to let our topmost CA, our root CA, be configured as a standalone root. Standalone servers aren't domain members. They do all their work offline. They're used to be able to create, principally, the certificates to be able to create new additional policy CAs, these middle manager CAs, and nothing else. Which means, once I've created certificates for those intermediate policy CAs, I can just turn off the root CA. If I want to be really secure, I can turn off the root CA. I can extract the hard drive from it, put the hard drive in a safe in the IT closet, put the actual computer chassis in some other closet somewhere. Is there any way that that system gets compromised? Nope, because the operating system is not even online. The computer doesn't even contain the hard drive that has the operating system, that contains the private keys associated with its own root CA. So building a CA chiefly involves making a decision of a standalone or enterprise CA, which is again largely determined by whether you've got Active Directory or not, or indeed if you're intending on leveraging Active Directory as part of the use of this particular CA. The second important question is identifying, are we starting a whole new hierarchy of certificate servers using this particular installation, or are we simply bolting this particular server onto an existing hierarchy of CAs? Before we go to install Active Directory certificate services on this server, it's worth noting that there is a potential shortcut of a sort. If I'm doing a large number of CA rollouts, I might look to be able to improve the consistency of my deployment of my CAs by automating certain parts of the installation. I do that by way of creating a file called capolicy.inf. Now this course is not going to go into extensive detail on how to configure a CA policy file. But in many cases, if I'm deploying a number of certificate servers, and in particular, if there are custom configuration settings that I want to see deployed consistently at each of those servers, and if I'm worried that I might inadvertently misconfigure one or more of them by doing the installation by hand, it probably makes a lot of sense to be able to create a CA policy file and use that to be able to do much of the deployment. Now, what goes in that file? Best resource that you'll probably find is a blog post done by the Active Directory Services team. You'll find it on the Microsoft website. Do a quick search on your favorite search engine, whatever it might be, and search for capolicy.inf syntax. And it'll take you right to the Active Directory Services blog, where the Microsoft Active Directory team writes regular messages about interesting subjects about the technology they're working with. And you can see section by section, key and value by key and value, exactly what pieces of data get supplied to identify the way my CA is going to operate. I can configure things like certificate lifetimes. I can determine the number of bits of encryption that I want to use for different kinds of encryption scenarios. That and lots more are all embedded in this text file. By putting that file in the C:\Windows directory, and doing so importantly before I start the installation of Active Directory Certificate Services, means that during the installation of ADCS, it'll find that file, read it, and configure the environment to take advantage of the settings that lie inside of it. So now I'll go ahead and make good on my promise to actually illustrate the installation process for a Server 2012 certificate server. So here I am on Server 2. We're going to roll out certificate services in this environment. I'm going to make this computer my enterprise root CA. I want it to be the logical starting point of all of the configuration inside of my internal environment. Now, by making it an enterprise CA, I'm essentially saying that I'm not going to be taking that CA offline. Enterprise CAs are members of the domain. They're presumed to be online more or less all the time. They're going to be able to field requests for certificates from clients from other servers in the network. They're presumed to be available. That would be appropriate for a small organization. If you're a reasonably small company, you're deploying certificates pretty much entirely for in-house consumption, then having an environment where this might be your only CA is probably a reasonable thing to do. Larger organizations are going to build an offline, standalone root CA. That computer is not going to be a domain member necessarily. It's going to be configured as a CA. It's going to be used to create the certificates for subsidiary CAs. And then, to be able to comply with security best practices, we're going to shut that computer down and put it in the closet. We'll take its hard drive out and put it in some other closet. But in this case, we're going to do a nice, simple enterprise CA scenario. So my starting point, of course, is going to be to install the software. So let me go to Add Roles and Features. Certificate Services is what Microsoft terms a role in this scenario. Roles are the important stuff. I might dedicate a whole server to it. Features are the ancillary benefits, the additional features I might use to help support the roles. I'm going to install it on Dallas Server 2. I'm going to deploy, there it is, Active Directory Certificate Services, ADCS. Do I want to include the management tools? Sure. Real world, I might prefer to just install the server components and put the management tools on a client machine, but in this case, perfectly sensible to include it here. Next question, do I want to put any features on this server? In this case, no. Of course, having chosen the client tools in the prior step, we would see if we scroll down inside of the remote server administration tools down here, we would see that we had chosen the client components for this, but that's already been accomplished. So we'll go ahead and click Next. As usual, Microsoft gives us a description of what Certificate Services is and does, why we might want to use it, IPsec, Network Access Protection, EFS, email encryption, SSL, lots of good reasons for using certificate services. Clicking Next brings us to the opportunity to choose additional role services. These are add-on features of ADCS that fulfill a number of different roles. The centerpiece, of course, is the Certification Authority, the CA. That is the brains of the outfit. This is the software that makes certificates available. It fields requests from clients. It publishes a CRL, a certificate revocation list, a list of those certificates that have been banned from use for one reason or another. The next piece is the CA Policy Web Service, which in conjunction with the CA Enrollment Web Service provide the two edge servers, if you will, for certificate services. By which we mean these are servers that I might choose to place in a DMZ to give them exposure to the internet, principally because I want to do certificate tasks not only from inside of my environment, but sometimes from outside. So you can see in the description off to the right there, the CA, the Certificate Enrollment Policy Web Service, lets users obtain enrollment policy info, the rules about getting certificates, even if you're outside of the network. We're connecting in via the internet, and this server is waiting there in what's sometimes called the DMZ. You'll see Microsoft will sometimes call it the perimeter network. The Certificate Enrollment Web Service is another edge server. It sits in the DMZ, sits in the perimeter network. Its job to be the server that fields the requests to actually enroll for certificates, to say, hey, I want one of those certificates. Can I have it, please? The Certificate Authority Web Enrollment is actually a web application that provides an internal to the company user the ability to connect to this CA and issue a request for a certificate via a web interface. Alternatives would include calling the CA administrator and supplying details about the certificate that you would like over the phone. But in some environments, a self-service option is a good one, and the CA Web Enrollment form provides that ability. NDES, Network Device Enrollment Service, is all about assigning certificates to hardware gadgets that run your network, routers, switches, other devices, where I want to be able to encrypt the communication to those devices. Well, if I want to do that, it would be sensible to be able to supply a certificate for those computers to do that encryption, public-private key encryption. It's a neat technique. And lastly, something called an online responder. There have been challenges over the recent years with the amount of stress being put on certificate services, specifically with the number of checks to see if a particular certificate is valid or not. It's possible to offload some of that responsibility to another server by installing onto it the Online Responder feature, giving clients an alternative target to go check to be able to ask questions about whether a certificate is valid or not. In this case, I'm just going to roll out the top option, the Certification Authority. We're ready to install. I'll go ahead and click Install. Deployment of certificates has been analogized sometimes to getting a driver's license from the Department of Motor Vehicles, or whatever they call your local driver registry facility where you are. You supply credentials to the DMV, and in trade they provide you with a document, something that binds your identity to information that is going to be identifiable by someone who wants to validate your identity, like a police officer. That individual trusts the DMV. The DMV has validated your identity. They trust that you are who you say you are. Therefore, the officer can trust that you are who you say you are by supplying that certificate. We're creating a somewhat similar environment here in Certificate Services. So having finished the installation, we do need to complete that configuration. We've installed the binaries, but we've not yet configured the details of how this server is going to work. So I'll click the link to configure ADCS on this server. It invites me to confirm that I am a member of appropriate groups that are relevant for the particular features that I want to install. In some cases, I need to be a member of the Local Administrators group. In other cases, I need to be a member of the Enterprise Admins group. Enterprise Admins are by default a member of the Domain Administrators group of every domain in my Active Directory forest. And it's that credential that's required for some of the more sophisticated, some of the more broadly impactful features of ADCS. The deployment of my web services are putting technology in the DMZ in a way that's going to, if it's not configured properly, it's going to make my network more vulnerable. That's something that requires somebody with a fairly high level of privilege. On the other hand, if I'm creating a standalone CA that's going to apply to this server and it's not an enterprise CA, it's not integrated with Active Directory, I can get away with just being a local admin for that purpose. In this case, I'm going to do the work as Domain Administrator, globalmantics/admin. I'm going to click Next. Wants to know which role services I'm configuring. I only installed the one, so we'll choose the one that's appropriate. Having done that, we'll click Next. It wants to know which type of CA I'm using. And in this case, for my purposes, I'm going to choose Enterprise. Enterprise CAs, it does point out, need to be members of the domain. They're integrated with Active Directory. They will be making certificates available probably by way of leveraging the group policy feature of Active Directory. Clients will be able to call the domain controller and say, hey, could you help me find a certificate server? And the domain controller says, oh, sure, Dallas Server 2 is a certificate server. Go talk to that guy. Standalone CAs, you'll recall, is the alternative. Standalone CAs can be made offline, and that's one of the main reasons for choosing a standalone CA, is to have an offline route. Offline servers can't be compromised through any sort of a network attack. And because that server's sole goal is to be able to authorize the use of other servers, once that's been accomplished, it's a security best practice to take the root offline. Those of you that saw the first Mission Impossible movie, remember the secure computer that the secret agent needed to get into in order to save the day. That computer wasn't networked. It was a standalone root of a sort. They had an online root. I would have turned that computer off if it were me. But anyway, let me re-choose Enterprise CA and click Next. I've got my choice of a root or subordinate. Subordinate CAs lie beneath some other certificate authority. That CA might be a root, or it might be yet another subordinate. It might be that a subordinate is 2 levels below the root, or 3 levels below the root, although that would be somewhat rare. A 2-tier or a 3-tiered scenario is fairly common, with a root at the top, and one or more policy CAs as subordinates to the root, each of which with different sets of rules for deploying different kinds of certificates in different sorts of ways, maybe in different regions of the world. And those policy CAs then enable the use of the issuing CAs, the ones that actually make available the certificates that are used by individual users and computers and services and such. So in this case, my first CA is going to be a root CA. Next question, where is the private key coming from? We identified that one of the major tasks of a public key infrastructure is managing the relationship between public and private keys. Public keys are shared broadly. Private keys are kept internally. The private key really is a local identifier of the individual who owns that key. To have the private key is to have a piece of information that makes it perfectly clear to someone that you are that user. So that information needs to be kept carefully guarded. But furthermore, if I decommission an old CA and move over to using some new CA, I would like to ensure that the idea of identity rolls from the decommissioned server to the new one. I don't want to have to recommission all of my certificates just because I changed certificate authority servers. This bit of interface provides that ability. I can either create a new key in a case where I'm creating a new CA from scratch. Perhaps this is an environment in which I've never had a CA. This is my first one. Alternatively, I can choose to reuse a key if I have one. Again, perhaps if I've decommissioned an old CA, I can take the existing private key from that certificate authority and import it into this one. I can pull that data in from a digital certificate, or if I've already imported that certificate, I can identify the existing private key on my system and say, yep, that one is me, that one is this server. In this case, this is a brand new CA, so I'll choose that topmost option to create a new private key. My next set of questions get very deep into the nerdy details of cryptography. And I encourage you to do outside reading on the technical details of how cryptography works. I filled in some of the basic details as we introduced this module. I filled in some of the basic details for you as I introduced this lesson. But you'll recall that the creation of a asymmetric key pair, a public and private key pair, requires the generation of a lengthy number. I get to choose how large of a key I want to use for those purposes. The larger the number of bits in the key, the more secure it is. On the other hand, the more processor intensive it is to encrypt and decrypt data using that key. The larger the key is, the more time it takes the certificate authority to generate a key of that sort. It's possible to generate a key of a size of 16,384 bits and spend a day to do it because it takes that much processing power to calculate the large prime numbers involved in that sort of an operation. Left of that is a choice of a cryptographic provider. A provider is a package of software to be able to perform all the operations that a CA does under the hood. Encrypting data, storing keys, decrypting data. We'll see that a cryptography provider may also provide one or more of what are called hashing algorithms. And different providers take different approaches to how many bits of encryption are used for each of those various different algorithms that are used to be able to make cryptography work. So for the purposes of our demonstration here, I'm going to choose the Microsoft Strong cryptographic provider. It identifies which signing hash algorithm do I want to use. When a CA produces a certificate, that certificate gets handed over to somebody. That person can use that certificate to say, look, the CA says this is who I am. But that only is meaningful if the person who receives that certificate has some way to validate that that's true. We don't want to be able to be passing around the equivalent of fake IDs in the certificate authority environment. We want actual legitimate driver's licenses. Well, how do we do that? Well, how does a police officer validate that you've handed him or her a correct driver's license? Well, there are technologies built into the way that the license is constructed that a police officer can verify that are hard for ordinary people to recreate. Symbols that only appear under certain customized kinds of light, holograms, things of that sort. There are ways to authenticate that that certificate, if you want to think of it that way, the driver's license, came from an authorized certification authority, the Registry of Motor Vehicles. What's the equivalent in the CA world? Well, that's something called a hashing algorithm. I can take a large piece of digital data and run it through an algorithm that scrunches it down to some typically smaller piece of data. The smaller piece of data is a representative of the large piece of data in the same way that the Cliff's Notes summary of a piece of literature is a representation of the original. But like that same relationship, I cannot work my way back from the compressed, summarized version of that data back to the original. But what hashes are good for, although clearly not for compressing and uncompressing, what they're very good for is for digital identification of data. If I take a large piece of data and I run it through a hashing algorithm, what comes out is some small piece of data that almost certainly could only have been produced by the input of the original piece of data. If I run a piece of data through that same hashing algorithm that is even in the slightest different from the original piece of data that I used in my example here, the output hash is wildly different. Hashing algorithms deliberately produce dramatically different results, even for very, very similar inputs. And as such, the hash that I do end up with is kind of a thumbprint of the original data that I started with. When a CA issues a certificate to somebody, that CA is going to associate the hash with that certificate, and it'll encrypt that certificate using its own private key. Someone can validate that that certificate definitely came from the CA when they can decrypt it using the public key of the certificate authority, which of course everybody has because it's public. At that point, the current content of the certificate can be rehashed using the same hashing algorithm, and that rehashing can be compared against the hash that the CA supplied. If those hashes match, we know that that certificate has not been changed in any way. There hasn't been any damage to it. It hasn't been tampered with by somebody trying to trick us into thinking that there's somebody that they're not. So we get our choice of a number of different hashing algorithms: secure hash algorithm 1, message digest versions 2, 4, and 5. Again, our choice of which hashing algorithm is best for which purposes is a discussion best saved for another time. For our purposes, I'm going to choose the popular message digest 5 format, and I have an option to allow the ability for an administrator to be involved in a case where we're going to be doing any sort of work that's sensitive related to the private key associated with our CA. Having done that, I'm going to click Next. We need to supply some identification information about our CA. It's going to have an identification within the overall network. It needs a name. CAs are identified first and foremost by something called a common name. And in general, and by default, Certificate Services is going to choose a CA common name that embeds the name of the domain of which it's a part, if it's an enterprise CA, the name of the server itself, and the term CA. Now I could choose some other name if I chose to, but in many cases that's very neatly descriptive. It helps me locate that CA later. If I give it some clever, creative name, I might struggle later to try to remember on which server I had installed the CA. Beneath that is a description of a distinguished name suffix. A DN, a distinguished name, is an LDAP style name. LDAP is the underlying database structure that supports Active Directory. So we can see here that when we put all those pieces together, we end up with an object whose common name, the name of the individual server itself, is GlobalMantic's Dallas Server 2 CA. That server sitting inside of a container whose domain component is GlobalMantic's and whose other domain component is local, or in other words, the globalmantics.local domain. What we're looking at here is a sophisticated Active Directory way of saying that this server is GlobalMantic's Dallas Server 2 CA dot globalmantics.local. That all looks fine. I'm going to click Next. The next question is, for how long will certificates generated by this CA be valid? Because these keys are protected by a strong asymmetric encryption, a public key infrastructure encryption model, I can deploy these certificates for quite some number of years without risk of somebody compromising those certificates and being able to misuse them. So I get to choose the amount of time. It might be some number of days or weeks if I want to be able to cut things down to renew that quickly. This calculation will be determined by things like, what's our current threat environment? How strongly are we likely to be attacked by the bad guys? If you're a large multinational corporation, probably a lot. You're a big target. If you're a small mom and pop shop, maybe you're less vulnerable. But in any event, we need to think carefully about the operating environment in which our certificate server is going to be doing its work. So in this case, I'm going to leave the default of 5 years and click Next. Certificate authorities store their information in a database, much in the same way that a SQL Server database does, or other database-driven applications like domain controllers. That database has to live in a particular location, as does the companion transaction log file. Many server-based database applications don't use just a single file to store their information, because for performance reasons, it's challenging to do all of our writing to the original database file. There's a lot of processing involved with accessing a database file. I need to gain access to the database file. I need to lock the portion of the database that I want to change. I need to make my change, release my lock, and disconnect from the database. That's a lot of work. So what a lot of database servers do, and the CA database is no different, is that it writes changes first to something called a database log. Now this isn't a text error log that you can read. Now this is a binary encoded summary of the changes being made to the database. Those changes are written to that file in that location, and periodically, when the CA server isn't busy, it takes changes that have been written to the log file and commits them through a process called checkpointing into the main database itself. I might consider, for performance reasons on a heavily used CA, the idea of putting the CA database on one physical disk and the transaction log on a different physical disk. If I've got two different physical hard drives in my system, I can improve the performance of that system by doing that split. And the reason that helps is because when I want to go commit changes from the transaction log into the database, I can be reading from the transaction log at the same time that I'm writing changes into the main database. Those things can happen in parallel. Contrast that against the scenario where I've got the database and the transaction log together on the same physical hard drive. I can only read or write at any given time on that disk. So if I want to take a change out of the transaction log and write it into the main database file, I need to do a read and then a write, and then I can go get the next piece of data off the transaction log, read that data and wait, and then write and wait. The technical term for that is drive contention. I've got multiple processes contending for access to that disk that are essentially fighting each other for the ability to perform what tasks they have been asked to do on that drive. Multiple physical disks will definitely improve the performance of database applications of this sort. All that done, we're ready to confirm all the changes that we've made. I'm going to click the configure button and off it goes. So this next part of the video is going to take a minute or two here, but here's what I'm going to do. I'm going to push the magic train signal button, and this is now going to run much faster than it would in real life. And there we go. Now don't forget that I could have automated some interesting chunk of this installation if I had created a properly configured capolicy.inf file. And we're going to put that file at the root of the c:\Windows directory before I start the installation of the certificate authority. If I do that, the installation process will take up that file and apply the configuration settings that are in it. If I've got a large number of CAs to roll out, it's a great way to ensure consistency in the installation of all of those CAs. I definitely don't want to get to the end of a national rollout of a PKI and find to my surprise that one of my CA servers is acting very differently from all the others. Because by the time I got to configuring that one, I was getting tired and made some mistakes. Yikes. I can pre-configure, if you want to think of it that way, many of the interesting configuration settings of a CA in that capolicy.inf file. So again, by all means, review the documentation around how that file gets created. Search for capolicy.inf syntax, and you'll find it on Microsoft's Active Directory blog on the Microsoft website. I'm going to click Close here. I'm going to close up my Roles and Features wizard, and I now have a certificate authority. What do I do with it? Well, to be able to take a look at it, I can go to the Tools menu, and I now have a Certification Authority item in that menu. And there we are. The Certification Authority is up and running. It is ready to receive some set of pending requests, which it will process and turn into issued certificates. Unless, of course, that enrollment for that certificate fails in some fashion, in which case it becomes a failed request. Those certificates will be handed out to individuals, and we will urge them to be careful to safeguard their private keys, but inevitably some of them will inadvertently do something foolish with them and leak that information, in which case we'll then find those certificates and revoke them, and they'll drop into the revoked certificates container. And as we identified back at the first slide that described this CA process, those certificates are generated based upon something called certificate templates. And those certificate templates identify the kinds of certificates that are relevant to roll out in my environment. So I get a phone call from somebody who wants me to create a certificate for them. I've now got a tool with which to do exactly that. So I hope that gives you a good backgrounding in what a certificate authority is and why you would want to use one. And I look forward to sharing more with you about how to configure your CA and deploy certificates that will serve your organization's purposes in other lessons.